So most of you have seen amino acids in biology, but we're going to focus primarily on the chemistry side, not the protein side. And in order to make an amino acid, or sorry, a protein or polypeptide, you need an amino acid building block. And if you remember, amino acids can be identified by the identity of the R group coming off that backbone, right? So there's a whole bunch of natural and unnatural amino acids, and we'll go over those in a minute. But the whole idea with this is you can link a bunch of these together in order to form a polypeptide. Bear with me. And I'm going to stop after this. And just like with any polymer, you can repeat this some number of times, and depending on the identity of the amino acids, you can get an infinite number of combinations, right? That's why this is such a powerful building block in biology, is it's incredibly versatile, both in terms of hydrophilicity, hydrophobicity, and its ability to do things like cross-linking. So this is just referred to as a polypeptide. The individual starting materials are called amino acids. All right, anytime you look at these, it's important to identify the peptide linkages or amide bonds. So for example, right here, that's a new amide bond that was formed. So oftentimes this will be referred to as a peptide linkage. Or a peptide bond. Make sense? All right, I forgot to print this out for today, but I'll have it ready for tomorrow. This is a common guide to the 20 amino acids. I pulled this off the website Compound Chemistry. He does a really good job of making things look pretty clean and organized. And you may notice on the top, he's got different symbols. He's got ones for aliphatic, aromatic, acidic, basic, and so on. And then he's got both essential and non-essential amino acids, depending on whether or not they're dashed. I would recommend hanging on to this for your biochem class. It's a really quick, easy to follow guide for identifying amino acids. The other thing to note too, is I'm going to zoom in even further. So let's take alanine. Alanine can be represented a few different ways. You can represent it with the symbol A, or you can represent it with the 3-letter code ALA. So basically, biochemists like to shorten down everything so it's easier to read a polypeptide that's maybe 10,000 units long. In that case, they probably use the single-letter code rather than the 3-letter code. However, that you may occasionally see the 3-letter code too. The other interesting thing too is if you take biology, you've probably seen these 3-letter codes. Those are the DNA codons that are required to make that specific amino acid. So this is all closely related to biology. All right, so for the exam, I want to make sure that everybody has all of these memorized along with the 3-letter codes. It's a joke. You may have to memorize them for biochem, so I'm not going to put you through that now. But I just wanted to show you the diversity of different amino acids, and I'll try to have this printed off in color for you on Monday. No. Really, all I'm concerned with as an organic chemistry instructor is teaching you the chemistry behind this. I don't want you to brute force memorize your way through all the names. That's silly in my opinion. All right, amino acids can actually be drawn using a Fisher representation, so I'll show you that. Let me zoom out. So in Fisher rep. All right, so I'll show you a common example of how to draw an amino acid. So for example, you always put your carboxylic acid off the top. And you put your R group down here, sorry. And then you've got a hydrogen here. And your amine over here. So the R group identifies the amino acid. So let's take an example. I'm just going to make up an R group, and we'll try to find the amino acid that corresponds to it. So I'll just do an easy one. We'll do a CH3 group coming off that R position. If we go back up and we look at the table, we've got to identify an R group that has a methyl group coming off of it. If you do that, you can quickly see, hey, this one over here has a CH3 group coming off of it, so it must be alanine for this one. So you can quickly use these tables to identify an amino acid. So let's go down and we'd say this is alanine. All right, and just like with carbohydrates, we said that D carbohydrates always have the OH on the right or the left-hand side? On the right. Okay, in this case, if you notice, the amine is always coming off the left-hand side. That means that all of these are L. So if we're describing this, we would say this is L-alanine. So the L means it's off the left-hand side. I'm just going to write L in parentheses so we can keep track of that. Does that make sense? So all natural amino acids are L amino acids. And there's been a lot of interest in the opposite one. So what happens if we have D amino acids? Because just like with sugars, I said with sugars, they're actually no-calorie sweeteners in some cases. So what they did was they started investigating these D amino acids, and I thought this was really interesting. These people started dying in China, and they couldn't figure out why, and they had a huge team trying to figure out what was going on to see if it was some sort of disease or something in the water or some sort of pollutant. What they narrowed it down to was these mushrooms. What they found is that these mushrooms actually make some amino acids. They're shown down here. And these are actually the wrong-handedness for your body. Your body kind of freaks out when it sees these and starts to shut down. So they actually poison themselves with some of these non-natural amino acids. So it is important that we have exclusively L amino acids, or else your body might not handle it correctly. The other thing that throws people off too is if we look back at the stereo center here, people will say, is the stereo center always R or is it always S for these? What do you think? So just think about a generic amino acid. Is it always going to be R or is it always going to be S? It depends on the R group. That is why we don't like using R or S, is it's not always going to be R. Sometimes it's R, sometimes it's S. It depends on the priority of the R group. So don't worry about R or S. Just take it with the case-by-case basis and then look at the molecule and do it the old school way of assigning priorities. Make sense? All right, last thing before we head out is the amino acids I've been showing you actually do a bunch of acid-base chem. And we'll talk more about this later. Let me zoom out a bit too. So I've got my amino acid like this. You think about this in your body, do you think it's going to stay as a carboxylic acid? Oh, we've got an issue here. This is an acid down here. This is a base. So in your body, essentially you'll have this shuttling of protons that move around. Before you know it, you're going to deprotonate your carboxylic acid. That's your carboxylate salt. And your amine will get protonated to form an ammonium ion, right? In this case, because you have both positive and negative, what would we call this? Zwitter ion. Or Witter, how do you say it? With the German accent? What would you say? I know. Witter? Zvita? I'm not sure. All right, we'll stick with one that's probably incorrect. All right. So the last thing, I'll do it as American. Zwitter ion. All right. Table 25.2 lists the pKa values. For various carboxylic acids, meaning every amino acid, that carboxylic acid has a different pKa. And because it's not going to list the pKa value of a base, it instead lists the pKa value of the conjugate acid. It'll list the pKa value for the ammonium ion. Oh, I'll just erase this one. So when you are looking at the pKa values, essentially what you're looking at isn't off both starting materials. Instead, you're getting a pKa value of your carboxylic acid and the ammonium ion on the physiological side. So it is a little bit confusing navigating that table, but you can't really have a pKa value for base. So instead, they give you the pKa value of the conjugate acid. All right, that's where we're going to stop today. When we go back on Monday, we'll talk a bit more about the reactions of amino acids.